Good morning, good afternoon, welcome everyone to my talk on cover spin textures in amorphous iron germanium thick films. My name is Robert Streubel. I'm an assistant professor at the University of Nebraska-Lincoln and will present this very exciting topic which was carried out in collaboration with Florence Berkeley National Laboratory, including in particular Materials Science Division, Advanced Light Source at the National Center for Electron Microscopy, as well as also the University of California, Berkeley. These projects were primarily supported by the Department of Energy, Basic Energy Sciences within the Non-Equilibrium Magnetic Materials program at Berkeley Lab, as well as also supported by Nebraska EBSCO. Now, why would it be interesting to think about topological magnetism, cover spin textures in amorphous materials? Well, one primary aspect is to think and further our understanding of this topic and really addressing three misconceptions in the magnetism community. The first is that small topological states require a large Jalusinski-Maria interaction, which is a vector exchange interaction in condensed matter. Now, the example of inversion symmetry broken B20 manganese iron germanium nicely showed that this is not the case. Now, moving from 100% iron to 100% germanium down to 50% manganese, 50% iron to 100% germanium, we clearly see that the size of those trigonal-skyrmion lattices scales inversely with the Jalusinski-Maria interaction. So that checks the box. However, manganese germanium has a much smaller Jalusinski-Maria interaction and should therefore have a larger skyrmion size, if at all. What we can see, however, from those images is that both the size further changes, decreases by at least a factor of 3, as well as also the symmetry changes from a trigonal lattice to a cubic skyrmion lattice. And this was always puzzling to the community until ab initio calculations revealed that those topological cubic structures can actually be simulated only by vector spin frustration without any Jalusinski-Maria interaction. So we can also stabilize small topological states without DMI, which in some cases are even smaller and therefore better for magnetic fundamental research, as well as also for spintronics applications. The second aspect is that a random local inversion symmetry breaking typically breaks down and vanishes in amorphous materials due to short-range order. While our results, as well as also independently other groups, showed by using rare earth-based soft magnetic materials, specifically gadolinium cobalt and gadolinium iron cobalt, that the Jalusinski-Maria interaction actually persists and is quite remarkably large in amorphous bulk materials. Using Brownian-like scattering, we further saw that the spin chirality, which is or can be derived from the difference in the frequency, shown at the bottom, actually reverses as we cross the compensation temperature, which means temperature can actually be used to control magnetic properties of domain walls in those amorphous materials, exactly what we postulated a couple of years ago by direct imaging of amorphous materials. And I will talk about this in a sec. The third aspect is that Barry curvature exists only in crystalline materials, as it is directly bound to a band structure which is not existent in disordered amorphous materials. Well, we showed both experimentally as well as also by ab initio calculations that all that matters is the density of curvature, and this can be calculated by the spin-orbit correlations of local orbital states, meaning that short-range order is all that matters, and raises a very interesting question about harnessing local inversion symmetry breaking for topological magnetism and spin orbit coupled materials. Now this can include obviously amorphous disordered materials, but also any material which has inhomogeneities, heterostructures, and interfaces which are typically disordered. Curvature and strain and even voltages break inversion symmetry, or also nanostructures, whether it's a helix, a tube, or a rod. All those systems have emerged and will emerge in the future as very interesting systems that locally break inversion symmetry. And the interesting part about that is that we could launch novel and enhanced functionalities which could severely benefit prospective applications in, for instance, microelectronics based on spintronics and spin applications. Now, another point is that we would have a much greater flexibility in material science, as we can choose more or less freely substrate, geometry, and composition, which is not the case with epitaxial or single crystalline materials. And the short-range order affects electron orbital hyperization, band structures, barrier curvature, as well as also spin-orbit coupling, which is essential to correlated systems, quantum materials, and topological magnetism. And one aspect which we went further to explore was really to investigate spontaneous inversion symmetry breaking in amorphous materials, which were predicted by micromagnetic simulations some time ago to stabilize topological chiral structures, which are isotropic but also anisotropic, including even topological knots. Now, the first step towards this direction was to investigate amorphous ferromagnets based on gadolinium cobalt. Gadolinium cobalt had been investigated for quite some time for all optical switching purposes and is also quite interesting as it has a very low spin damping and is therefore attracting interest from spintronics and magnonics point of view. Now, we further used heavy element materials such as platinum and iridium to really induce interfacial inversion symmetry breaking and an interfacial DMI, Germanium interaction, on cobalt. And by doing that, we further visualized the magnetic domain walls in those out-of-plane magnetized materials, where we use phase contrast imaging with high-resolution Lorentz microscopy to reconstruct the exit wave. And the top row shows the electron phase. The bottom row shows the in-plane magnetic induction, or in this particular case, the magnetization. And what we see there is that we have quite a difference in magnetic contrast and magnetic domain types and chirality. For the symmetric stack, we observe an achiral Bloch wall. For the asymmetric stack with interfacial Germanium interaction, we observe chiral spin textures, which are Néel or Néel-Bloch hybrid walls, which depends on the saturation magnetization. So the domain morphology, meaning size and shape, is depending on saturation magnetization, as we know from ferromagnets, and the chirality and the type is depending on the vector exchange interaction. And since the saturation magnetization can be nicely tuned in ferromagnets by temperature, we postulated that the internal structures, including chirality and type of domain walls, can actually be tuned by temperature, and more importantly also that vector exchange persists also in disordered amorphous materials consisting of quite complex system where cobalt is a direct exchange coupled materials and gadolinium is an indirect exchange coupled materials. And this was confirmed, as mentioned earlier, by Prion-like scattering. From this starting point, we then further wanted to altogether remove interfacial effects and really thinking about bulk materials where it is all about the local inversion symmetry originating from disorder in amorphous iron germanium thick films. And I would like to guide you to those two very interesting publications, one in Advanced Materials, which I will talk about, as well as also the Physical Review B, which was led by Sim Kabuma, focusing mainly on the transport properties, which is also highly interesting. Now those materials were co-evaporated at room temperature, and we chose film thicknesses of about 80 nanometers, which is sufficiently thin to perform transmission experiments with electrons and with X-rays, but sufficiently large to really minimize interfacial contributions, which typically only account to 1 or 2 nanometers. Now from small angle electron diffraction, we observe that there is no symmetry and truly only a short-range order. Magnetometry measurements revealed a very soft magnetic material which has a small in-plane preference due to the shape anisotropy. And the saturation magnetization revealed that the magnetic moments are very similar to crystalline B20 structures, which is very interesting to note, because this implies that we actually have a very similar local atomic environment. Furthermore, quantifying the orbital and the spin moment using X-ray magnetic circular dichroism spectroscopy, we observed a reduction in the orbital moment at certain temperatures and at low iron concentrations. And as you might recall, the orbital moment is a direct indication of the electron orbital alignment, and when we see a reduction in the net orbital moment, this indicates that the electron orbitals are randomly aligned, meaning disordered. Now those results we then further took into account when imaging our magnetization vector fields with Lorentz microscopy, which you can see on this slide, and where we assembled a magnetic phase diagram as a function of temperature and iron concentration. For large iron concentration, we observe, let's say, a trivial soft magnetic ferromagnetic state. At 60% iron and below, we observe a slightly disordered helical spin lattice, which is decorated with symmetric and isotropic Bloch skyrmions. And at low temperature, we observe insulated anisotropic skyrmions and also a low temperature phase, which shows a very small or vanishing magnetic contrast. Now this indicates those results that the Chiral spin textures, in particular the helical spins, emerge in systems and at certain temperatures and parameters where we observe a reduced orbital moment, indicating that we have to have a random orbital alignment to get spin frustration, which then stabilizes the magnetization. Now, another point what we further investigated was phase transitions and thermal spin fluctuations, particularly as we observe that the magnetic contrast is going away at low temperatures. Using Lorentz microscopy, we can visualize the in-plane magnetization. We can further calculate the two-dimensional Fourier transform of this real space image, which is shown at the right-hand side, but only for a certain area, which is referred to as a speckle pattern. And this is done to correlate it with coherent X-ray scattering, which probes the Fraunhofer far-field diffraction, which is mathematically or physically nothing else but a two-dimensional Fourier transform. However, X-ray scattering probes the out-of-plane component and Lorentz microscopy probes the in-plane component. But we observe that both the pattern and the intensity are behaving very, very similar, considering that it's the different area, a different sample, etc. So what does this indicate? It indicates that the system loses both short-range and long-range order at low temperatures, at least in the accessible temporal and spatial resolution limit, which is in this particular case about 1.1 seconds and about 5 nanometers or so. Now, why could that happen? Well, when we record actually the temperature at the time series and calculate the standard deviation, which displaces and visualizes the location and amplitude of thermal spin fluctuations, we observe first that those fluctuations are confined to a helix pitch and a skyrmion size, as well as also that they persist well beyond the phase transition, which is very indicative and characteristic of spin-frustrated systems, and that the lack of magnetic contrast is most likely because of an enhanced thermal spin fluctuation. This is further backed by our investigations of the low temperature phase at 110 and 100 Kelvin, where the time averaged signal does not show anything. It's basically gray, so no magnetic contrast. However, the standard deviation shows a very pronounced dipolar contrast, which means we have a frequent or quasi-periodic switching of n equals 2 skyrmions between, let's say, state 1 and state minus 1. And this is a state flicking between black and white and black. Now, when we conduct simulations, phase contrast simulations, as shown at the left-hand side, we observe that those two states are only mathematically rotated by 180 degrees, as they have a mirror symmetry. However, physically, they are distinct, as the local environment changes quite significantly in amorphous materials, and if you go from the center to the top, you see that one is left-handed, the other one is right-handed. And that we observe those frequent fluctuations indicates that we have a degenerate spin chirality and a particle-like property in those systems, which is very, very important and interesting to see. Now, the thermal spin fluctuations and the rate of those depends strongly on the location, which you can see at the right-hand side, indicating that we have quite spatial variations in exchange and magnetic anisotropy. From the histogram, we further reveal that this is actually a stochastic and temperature-driven excitation, so it's not an artifact, which is a good thing. So to conclude my talk, I showed you that amorphous materials are actually pretty interesting, not only from a perspective of phase change materials and all optical switching, but also from the perspective of topological magnetism and chiral spin textures, as they allow to stabilize isotropic and anisotropic magnetic solitons owing to atomic environments which is very similar to single crystals. And it could provide a route to synthesize multifunctional materials, and broadly they show that a well-defined symmetry is not required to stabilize topological vector fields. Now, with this, I would like to thank you for your attention and time.